So now we come to the last new kind of problem that we're going to be studying. It's called the nonlinear least squares problem, and it generalizes almost everything else that we've done during the course. So in this case, the problem is a function, capital F, which maps n variables to m variables. And here now m is greater than n. So we are we have more conditions or more objectives to specify than we have variables to satisfy them. And so we won't be able to satisfy all of the objectives exactly. Instead, what we have to do is kind of do the best job that we can of satisfying all those constraints at the same time. So if we think of the target as being setting each component of f equal to 0, we can't achieve it because we have too many components to do, given the variables. Then instead of setting them all equal to 0, we're just going to try to minimize them. And the minimization we choose is, once again, the minimum of the sum of squares. So we can just express that with the 2 norm as the norm of f squared. There's a factor of 1/2 to make some of the later calculations more convenient. Or we could think of this in terms of f transpose f. The inner product of f with itself, that's equal to the 2 norm. Or if we write it out, we have the sum of f1 squared plus f2 squared and so on. All right, so this really encapsulates a lot of the problems we've done so far. So if we have m equal to n, the same number of constraints as variables, and everything is linear, then we're back to the linear system of equations, which was the first kind of problem we solved. If m is greater than n and we have linear functions, then it's linear least squares. So again, we have to minimize something rather than setting it equal to 0, but everything is linear. If everything is nonlinear, but there's only one variable and one constraint, it's root finding. And if everything is nonlinear, but there are the same number of constraints as variables, then we have a system of nonlinear equations. So all of these different types of problems are, in some sense, a special case of this one. However, they're so special and so important that they have their own methods of being solved. So if we think for a minute about one dimension in order to get some ideas, we know that for a one-dimensional function in calculus, f of x, if f of x happens to be minimized at a point s, then s is a critical point of f. So either f prime is equal to 0 at s, or f prime doesn't exist at that point. Those are the only possibilities if f is going to be minimized. It's going to have a local minimum at s. So that means that if we rule out f not existing just by saying, well, let's say f is differentiable everywhere, then we know that f prime equaling 0 is necessary in order to have a minimum. All right? You can't have a minimum without it. But it's not sufficient, though. So, of course, right, we could, when at a point where f prime is equal to 0, we could have a minimum, or we could have a maximum, or we could have neither, like in the cubic function, right, where you have a horizontal tangent, but neither a local min nor a local max is possible. So you can't tell whether you have a minimum for sure until you check at least the second derivative. And so what we say about f prime equaling 0, we call it a first order, because it's a first derivative, necessary condition. It's a necessary condition in order for us to find a minimum, but it's not sufficient. You could have f prime equal to 0 and still not have a minimum. But for the most part, first order necessary condition is as much as we can check. And that's going to be our target in the multidimensional case. So in n dimensions, okay, if you have a function of n variables, now f, little f, let's say, just has a single real value, okay, but n variables. That's actually the situation we have, right? So capital F is a vector function. It has m components to it. But when we take the inner product of f with itself, right, this is a scalar quantity. It's a scalar function of n variables. All right, so in the general case, when we have a scalar function of n variables, we know from vector calculus that that function is minimized at a point if its gradient is equal to 0. So this symbol here is sometimes called nabla. Okay, so but we usually just read this as grad f, or the gradient of f, evaluated at s. And remember, the gradient is a vector quantity, so little f is scalar. The gradient of f is a vector. It's a vector of all the possible partial derivatives of f. Okay, so for example, we have this function of two variables, so we could compute its gradient. All right, so the derivative with respect to x1 and the derivative with respect to x2. Like so. And then, if that's the case, then grad f equaling 0 implies that x1 must be 0, and it implies that x2 must be negative 2. So that would be our first order necessary condition for a minimum. Okay, next example, example B. We have a very similar looking function. We can compute its gradient, so the derivative with respect to x1 is just 2 times x1. The derivative of f with respect to x2 is 3 times this quantity squared. And so if we require the gradient to be 0, then that implies, again, the first component tells us that x1 is 0, and the second component tells us that x2 is negative 2, same as before. So both of these examples have the same first order necessary conditions for a minimum. However, they behave very differently. So here's example A. And the point that we found, 0, negative 2, is this white dot here. So this is the point x equals 0, or x1 equals 0, x2 is equal to negative 2. And that's clearly a local minimum of this surface. But in example B, okay, it's not so easy to see, but the point is in the middle again. So x1 is equal to 0, x2 is equal to negative 2, right there in the middle, and it's clearly not a local minimum. So we have the exact same problem in multidimensional functions as we had in one dimension, that the first order necessary conditions, okay, don't guarantee a minimum. However, they tend to be the only thing that's practical for us to look for.